Students, in this video we are going to learn how to find the derivatives of implicit functions. Okay, but before I begin, let us discuss about what are implicit functions. Any function of the form f of x comma y equal to 0 will be called an implicit function. Okay, how do you identify an implicit function? It will be a function containing two variables x and y mixed together, and it will be given in the form of an equation. For example, this one. You can see here we have x cube plus 3x square y minus 2y cube equals to 5. Over here x and y are mixed together and it is equal to 5. So this kind of a function is called an implicit function. Got that? Another example of implicit function, if you have like this. Here it is an equation in x and y. So this is also an example of an implicit function. Understood? Okay. Now suppose this is your question. If this is there and find dy by dx. This is your question. Okay, if this is the value given to you, find dy by dx. So how are you going to get the solution of this one? We will begin by writing given x cube plus 3x square y minus 2y cube equals to 5. This is given to me. Okay. Now I will write differentiating with respect to x. We get, you have to differentiate both sides with respect to x. Okay. On differentiating, what will you get? On the left hand side, you will get d by dx of x cube plus d by dx of 3x square y minus d by dx of 2y cube equals to d by dx of 5. Correct? Okay. Now on differentiating slowly, what are you going to get? D by dx of x cube is 3x square plus d by dx of 3x square y. 3 is a constant, comes out, and d by dx of x square y is in the form of u into v. Now d by dx of u into v is u into d by dx of v. Correct? So this is x square into d by dx of y plus y into d by dx of x square. There you go. Okay. Minus d by dx of 2y cube. 2 comes out as a constant. D by dx of y cube. Let me write it down. D by dx of y cube equals to d by dx of 5. You know 5 is a constant, so it becomes 0. Okay. So next step. 3x square plus 3 into, inside the bracket you have x square into d by dx of y. X is a different variable, y is a different variable. So it becomes dy by dx. Plus y into d by dx of x square is 2x. Minus 2 into d by dx of y cube is 3y square into d by dx of y cube. Y is a different variable, so you are going to once again differentiate that y, because in place of x we have a y, so apply chain rule, you will have to write dy by dx in the end equal to 0. Done? Okay, opening your brackets, you have 3x square plus 3x square dy by dx plus 3 2s are 6xy minus 2 3s are 6y square dy by dx equal to 0. Correct? Now your task is to find dy by dx. The question says find dy by dx. So what I'm going to do is terms containing dy by dx I'll keep on the left hand side and remaining terms I'll take to the right hand side. Correct? So here I will have 3x square dy by dx minus 6y square dy by dx equals to 3x square becomes minus 3x square, 6xy becomes minus 6xy. Got that? Okay. Our next step is common, dy by dx common. So what will you get? 3x square minus 6y square dy by dx equals to, here I can see 3 is common, x is common. So I will have over here x minus plus 2y. Correct? Okay. Or now take this whole thing to the right hand side. So you will have dy by dx equals to minus 3x into x plus 2y upon this one 3x square minus 6y square. Correct? Now you can see that in the denominator also there is 3 common. So it can be pulled out as 3x into x plus 2y divided by 3 common, so you'll have x square minus 2y square. So 3 gets cancelled, therefore dy by dx equals to minus x into x plus 2y divided by x square minus 2y square. You can leave your answer this way. Okay, if you don't want the minus sign over here, what you can do is you can multiply the minus with a plus sign. The numerators minus can be taken out common. Okay, so it could be minus x into x plus 2y divided by minus 2y square upon minus x square. So this minus minus gets cancelled. You have x into x plus 2y divided by 2y square minus x square. This should be your answer. So dy by dx is this much. Got it? This is how you find the derivatives of implicit functions. Okay. Derivatives from parametric equations. Now suppose you are given parametric equations x equal to a cos theta and y equal to a sin theta. You can clearly see that theta is the parameter over here, right? If you are given two such equations and you are asked to find dy by dx, then how will you do that? Now, since my equation contains x equal to a cos theta and y equals to a sin theta, there is no way of finding dy by dx by differentiating any one of these equations directly. Isn't it? You cannot find dy by dx from here. You cannot find dy by dx from here. Obviously, x is over here, y is in the second equation. You have to combine the two equations in some way to find dy by dx. Correct? So, to do that, what are we going to do? In order to find dy by dx, since our parameter is theta, what we are going to do is dy by dx is going to be calculated as dy by d theta upon dx by d theta. Got that? dy by dx is going to be calculated as dy by d theta upon dx by d theta. You can understand it by imagining that d theta gets cancelled. Actually, that doesn't happen. Just imagine it, okay? Suppose d theta gets cancelled. So what will you be left with? Dy and dx. Obviously, you're going to get back your dy by dx, right? Just understand in that way. Actually, that doesn't happen, okay? You're not allowed to cancel d theta and d theta. Don't think that. Okay, just for your understanding base, just to keep it in mind, just think that d theta and d theta goes away and you are left with dy by dx. Okay, so I need dy by d theta and I need dx by d theta. So let us find over here. See, my first parametric equation is x equal to a cos theta and my second one is y equal to a sin theta. So what I am going to do is, in the first one, I am going to differentiate with respect to theta. What will I get? D by d theta of x equals to d by d theta of a cos theta. In the second one also, differentiating with respect to theta, what am I going to get? D by d theta of y equals to d by d theta of a sin theta. Okay, let me differentiate. D by d theta of x is dx by d theta. As simple as that. A is a constant, a comes out. D by d theta of cos theta is minus sin theta. You all know that, right? Therefore, dx by d theta equals to minus a sin theta. Similarly, this side I'll have dy by d theta equals to, a comes out as a constant, d by d theta of sin theta is cos theta. So, dx by d theta is minus a sin theta, dy by d theta is a cos theta. Now, I am asked to find dy by dx. Now, you know, dy by dx can be calculated as dy by d theta upon dx by d theta. So, let me put my values here. My dy by d theta is a cos theta upon my dx by d theta is minus a sin theta. So, a gets cancelled. My answer is minus cos theta by sin theta, which is equal to minus cos theta upon sin theta is cot theta. Got that? So this way I got my answer. Dy by dx is minus cot theta. Clear? So this way parametric equations are to be differentiated. First they are going to be differentiated separately according to their parameters with respect to their parameters, correct? Then after getting the separate values put back together in dy by dx, you will get your end result. Derivatives of inverse circular functions. Now, in order to find the derivatives of inverse circular functions, these are the 6 main formulas that you need to learn. The first one is d by dx of sin inverse x is equal to 1 upon root over 1 minus x square. D by dx of cos inverse x is equal to 1 upon root over 1 minus x square again, but with a minus sign. Okay, third one is d by dx of tan inverse x is equal to 1 upon 1 plus x square. D by dx of cot inverse x is minus 1 upon 1 plus x square. D by dx of sec inverse x is 1 upon x root over x square minus 1, and d by dx of cosec inverse x is minus of 1 upon x into root over x square minus 1. So these are the important formulas that you need to know from inverse circular functions. These are direct derivatives which you can apply in the form of formulas while solving your questions. Okay, now let us take some examples about how to use these formulas. The first one I've taken is 2 tan inverse x by a. Now, suppose you're asked to find the derivative of 2 tan inverse x by a. So, how are you going to do that? So, see, in order to find the derivative of 2 tan inverse x by a, you will write d by dx of 2 tan inverse x by a. Correct? So, its answer is 2 is a constant, comes out. So, d by dx of tan inverse x by a. Over here you can see you have to find d by dx of tan inverse x. Now you know d by dx of tan inverse x is 1 upon 1 plus x square. So I will write over here so that it is clear for you. Tan inverse x is 1 upon 1 plus x square. So here I am going to write 2 as it is. D by dx of tan inverse x by a is 1 upon 1 plus, in place of x I have x by a. So here I'll write x by a whole square. But now you know from chain rule that since in place of x I have x by a, I don't have x but I have x by a. So I need to redifferentiate it x by a. This I need to do. This is a very important part of your problem. Okay. So next step you will have 2 into 1 upon 1 plus x by a whole square is x squared by a square into d by dx of x by a is 1 by a common. D by dx of x is 1. Done. Next 2 into 1 upon, find the LCM, a square plus x square into 1 by a. Got that? Now this becomes 2 into a square by x square into 1 by a. A gets cancelled and you are left with 2a by a square plus x square. So this is your required answer. Got that? Okay, I'm going to take a similar question, a second one. Please see. Question number 2. Suppose your question is 2 sec inverse of 2x minus 3 sine inverse of x plus cos inverse of x square. I'm taking an example from your book. Okay. Now, how do I differentiate this one? Now, in order to differentiate this, I will obviously write d by dx of 2 sec inverse of 2x, d by dx of 3 sine inverse x plus d by dx of cos inverse of x square. Correct? Now, one by one, I'm going to differentiate this. Okay. Now, since you can see d by dx of 2 sec inverse of x. So, 2 is a constant, comes out. D by dx of sec inverse x. Now, according to the formula, d by dx of sec inverse x is 1 upon x into root over x square minus 1. So, here I will write 1 upon, in place of x I have 2x. So, x into root over x square minus 1. Done. But then since in place of x I have a 2x, so I'm going to differentiate it. D by dx of 2x. Done. Now go to the next one. Minus d by dx of 3 sine inverse x. 3 is a constant, comes out. D by dx of sine inverse x, we know it is 1 upon root over 1 minus x square. Clear? Now the third term, d by dx of cos inverse x square. Now again, d by dx of cos inverse x is minus 1 upon root over 1 minus x square. So that one I'm going to use here. So here, d by dx of cos inverse of 1 minus cos inverse of x square is minus 1 upon root over 1 minus x square. Because in place of x, you have a x square in the question. Okay, this is done. Into, since in place of x I have a x square, so I'm going to redifferentiate my x square. Got it? Okay, now open your brackets. You will have 2 into 1 upon, this one becomes 2x into root over 4x square minus 1 into d by dx of 2x is 2 minus 3 upon root over 1 minus x square plus into minus minus 1 upon root over 1 minus x square whole square is x to the power 4 into d by dx of x square is 2x. 2 gets cancelled, so you are left with 2 upon x root over 4x square minus 1 minus 3 upon root over 1 minus x square minus 2x upon root over 1 minus x to the power 4. This is your final answer. While finding out the derivatives of inverse circular functions, the most important thing that you need to notice and keep in mind is what is in place of x. When you see that there is something in place of your x, do not forget to re-differentiate it like this. Got that? Okay. Our next type of differentiation is logarithmic differentiation. Now, in logarithmic differentiation, when we are trying to differentiate given functions, we take help of logarithms in order to find the derivatives of the functions. Okay, for example, in this question, you can see the question says y equals to sine x to the power log x. It is in the form of function to the power another function. You can see that, right? Now, function to the power functions are difficult to differentiate directly. So what we will do is, before differentiating this function, what we are going to do is we are going to apply log on both sides. So logarithmic differentiations are usually used to remove function to the power function or make it more simple before differentiation. Got that? So how we are going to use it? See, since I have function to the power function over here, in order to get rid of this power, which is also a function, what I'll do is I will taking log on both sides. I'll take log on both sides. We get, what will I get? This side I'll have log of y and this side I'll have log of sine x to the power log x. Got that? Now when you do this one, you can see it is log y equals to this side you have log x to the power y. Correct? It comes in the form of log x to the power y. Now according to the properties of logarithm, log x to the power y could be written as y log x, power can come to the front. Correct? So I'm applying the same property over here, and log sine x to the power log x becomes log x. This power comes to the front and you have log of sine x. Got that? Just take this log x and bring it to the front according to the property. Got it? Now the power is removed. Correct? Now since the power is removed after applying logarithm, now you can differentiate it normally. Okay? So differentiating both sides with respect to x, we get, what do we get? Here, d by dx of log y equals to d by dx of log x into log sine x. Done. Okay, d by dx of log y, x is a different variable, y is a different variable. First of all, let us think about log differentiation. D by dx of log x is 1 by x, so obviously d by dx of log y is 1 by y. But then in place of x, I have a y, so I'm going to re-differentiate whatever is in place of x. So it is d by dx of y equals to, now d by dx of first function into second function. So d by dx of first function into second function is d by dx of log x is 1 by x into log sine x plus log sine x into d by dx of log sine x into log x. I hope you got this. Okay, chain rule. So this will be 1 by y dy by dx equals to, this becomes log sine x by x plus d by dx of log sine x is, again d by dx of log x is 1 by x into, in place of x I have sine x, so d by dx of sine x. D by dx of log sine x is, take it in the form of d by dx of log sine x looks like d by dx of, suppose this is x, so d by dx of log x is 1 by x. Got that? But then in place of x I have a sine x, so I re-differentiate that sine x as d by dx of sine x. Got that? Into log x. Okay, so this will be 1 by y dy by dx equals to log sine x by x plus this will be 1 upon sine x into dy by dx of sine x is cos x log x. So this will be 1 by y dy by dx equals to 1 by x log sine x. It could be written in a better way like this, plus cos x upon sine x is cot x log x. So this will be dy by dx equals to y into 1 by x log sine x plus cot x log x. Putting back the value of y, you will have dy by dx is equals to y means sine x to the power log x 1 by x log sine x plus arrange log x cot x. This should be your answer. Okay, this is how you differentiate with the help of logarithm. Okay, how to find the derivative of one function with respect to another function. Now children, for that you are given a question over here as an example. See over here. Your question is, find the derivative of x square with respect to log x. You have to find the derivative of x square with respect to log x. Okay, now how we are going to do? For this one, what I am going to write is, I am going to suppose the first function as y. Okay, and the second function as z. For that, suppose x square is y and log x is z. Now, if you are asked to find the derivative of x square with respect to log x, can I say I'll have to find the derivative of y with respect to z? Correct? So, derivative of y with respect to z. That means I have to find dy by dz. Understood? Now, in order to find dy by dz, my dy is here, my dz is here, y is here, z is here in two different equations. That means I need to combine these two equations together to get dy by dx. Correct? So first what I will do is, as simple as that I'm going to differentiate this equation and I'm going to differentiate this equation. You can clearly see on the right hand side the variable is x. Here also on the right hand side the variable is x. So I'm going to differentiate this with respect to x. I'm going to differentiate this with respect to x. So differentiating with respect to x, we get dy by dx equals to d by dx of x square, which is equal to 2x. Can I say that? Yes. So dy by dx is 2x. Clear? And over here dz by dx is d by dx of log x, which is equal to 1 by x. Correct? So from here I have dy by dx is 2x and dz by dx is 1 by x. Now from these two values I am supposed to find dy by dz. So therefore dy by dz could be calculated as dy by dx upon dz by dx. Can I say like this? Just imagine dz dx getting cancelled. So you have dy by dz. So from here my dy by dx is 2x. dz by dx is 1 by x, which becomes 2x squared. So the differentiation of x squared with respect to log x is 2x squared. Clear enough? Okay, this is how you find the derivative of one function with respect to another function. Suppose the first function as y, suppose the second function as z, and then calculate dy by dz. Simple? Okay, I'm going to take another example. Here you are asked to differentiate sine inverse of 2x upon 1 plus x square with respect to tan inverse of 2x upon 1 minus x square. Now you can see over here that these two are a little complicated kind of functions. They are inverse circular functions, but again in the angle part you have a complication, right? So we need to do something about it. But before that, let me assign y and z to these two functions. I will suppose let y equal to sine inverse 2x by 1 plus x square. And this side I'll write z equals to tan inverse 2x by 1 minus x square. Now since these are inverse circular functions and I need to get rid of the inverse sign, what I will do is, in this one, if I had with sine inverse, if I had sine of something, then sine inverse and sine will go away. Correct? Over here with tan inverse, if I have a tan of something, then tan inverse and tan will go away. Understood? So what I will do is I'll try to replace these values with, over here I'm going to replace this with sine of something, and I'm going to replace this with tan of something. But what? You know in the formula that sine 2 theta is 2 tan theta by 1 plus tan square theta. And tan 2 theta's formula is 2 tan theta by 1 minus tan square theta. Now you can see these two are exactly same. The only difference is in plus and minus. 2 tan theta by 1 plus tan square theta. Now if your tan theta was x, then this will be 2x upon 1 plus x square. 2x upon 1 plus x square. Oh, it's matching, isn't it? Again, over here, in place of tan theta, if you had a x, it would be 2x upon 1 minus x square. So here I have 2x upon 1 minus x square. So these two are exactly in the form of the formulas of sine 2 theta and tan 2 theta. Only problem is that in place of tan theta, I'm having a x. So if I write tan theta in place of x, then these two will be converted into trigonometric formulas, correct? So what I will do is I'll simply write let x equal to tan theta. Got that? So as soon as I write x equal to tan theta, what happens is this whole thing becomes y equals to sine inverse 2 tan theta by 1 plus tan square theta, which will be equal to sine inverse sine 2 theta, and sine inverse and sine go away and you have y equal to 2 theta. Immediately this side also it becomes z equals to tan inverse 2 tan theta upon 1 minus tan square theta. So this will be z equals to tan inverse of tan 2 theta. Tan and tan goes away, tan inverse and tan go away, you have 2 theta. Now it is simplified, correct? So, therefore, dy by d theta is actually d by d theta of 2 theta, which is equal to 2. And this side, dz by d theta is d by d theta of 2 theta, which is also equal to 2. Simple enough, right? So, my task is to get dy by dz. Now, can I get dy by dz from here? Obviously, I can get. Therefore, dy by dz could be written as dy by d theta upon dz by d theta. Correct? So, from here, since I have dy by d theta's value is 2 and dz by d theta's value is also 2. So, my answer is 1. So, my dy by dz is 1. Simple. Now, there could be a problem over here. Once you find your dy by d theta in some other problem of similar kind, in place of just getting a number, you could get something in terms of theta here, something in terms of theta here, and after cancellation, you could get your answer in terms of theta. But then in your original question, there was no theta. There was only x. Correct? So, what you will do is, after you find your original question, if you find something in x, what you will do is you will replace it by this one. Okay, your theta equals to tan inverse x. So wherever there is theta, you write tan inverse x. From here, it implies that theta equals to tan inverse x. So in the final answer, if you get something in theta, you just replace the theta by tan inverse x, and that will give you your answer.